Sorry if you're at home. I can't bring up my science book and record, so you guys will just have to stare at a blank screen and listen. Okay, so who can remind me what we talked about yesterday? Harper.
Force.
Okay, we talked about force. What is one kind of force? Abby?
Like pulling.
Okay, a pull. Kendall? Or a push. Pushes and pulls are some types of forces. Yesterday, what we ended on was a contact force. Which category do you think push and pull? Do you think they are contact forces? Why? Why do you think they are contact forces? Abby?
Because you have to,
Yeah, for me to push Maya, I have to contact her. Okay, my hands have to come in contact with her body somewhere for me to push her or to pull her. So the two that we talked about yesterday are both contact forces. What else did we talk about besides force? Kendall? Motion. Okay, motion is just a fancy word for any type of movement. Okay, so in a nutshell, that was yesterday. I believe we are on we finished up page 62, and we're on page 63. Is that correct?
I think you finished it. No, we didn't.
Nope, I don't think we answered the questions.
Yeah, we did.
No, we did not. Parker, that's on page 62. Okay, yeah, so we are on page 63. We've already read all of the text. There's just some questions on page 63. So our goal for today is get through pages 63, 64, 65, and then fill out the foldable that you glued in yesterday. If we get through all of that, you guys will have no homework tonight, okay? If we get through all of that and have time, we're going to get out our vocab cards and start numbering them like what lesson they go with. So we'll just pull out the lesson 1 ones and put a 1 on them. Okay, so page 63 at the top, up by the rollerblade, it says, the large amount of friction between the tires and the track make it harder for cars to slide out of control. Friction also causes the brakes on the back of an inline skate to slow or stop the skater. Explain, how do brakes help an inline skater stop? First, if you're wearing skates, are you just going to stop all of a sudden?
No.
What do you have to do first? Brady?
You have to kind of plant your foot.
Yeah, you kind of have to tilt your heel, so you have to move your foot, right? In which way? To make the heel kind of touch?
Are we talking about ice skating or
The skate in the picture, so like a rollerblade.
Oh, yeah, you just tilt your foot back.
Okay, tilt your foot back. When you make that movement of your foot, how does that stop you or slow you down? Reese?
There's a brake on the back of the rollerblade and then
Okay, so there is a brake there, but why do you stop? Sadie?
Because the brake is hitting the ground, it's causing friction.
The brake is coming in contact with the ground, which causes friction. Okay, it's science. It's common sense, but it's science common sense. So let's write that up on number 4. So when you tilt your foot, we won't put backwards, we'll just say when you tilt your foot, the brake comes in contact with the ground. Creating what? Friction. Okay, and it makes sense. We just had to add some new vocabulary to that. So then down at the bottom it shows 3 guys on a pit crew. What's a pit crew? Parker?
The only changes the tires and gas is the driver's race car.
Yeah, so they're the people who change all the stuff that needs changed on a race car in a very short amount of time. So they use all different kinds of forces to do their jobs. It shows the guy in the back is pushing down on a lever so that he can lift one side of the car. So it's a jack. So if he pushes down, it pushes the car up. The one kind of kneeling, I'm going in the box on the car, says this member of the pit crew is pulling a worn out tire off the car. So the one guy's pushing down, that's one force. The other guy is pulling the tire, that's a different kind of force. And then it's talking about their shoes. Many shoes have rough soles that increase friction with the ground and prevent slipping. Why do you not want to wear cowboy boots in the winter? Abby?
If it's snowing, then you
Yeah, especially if it's icy, okay? There's no, cowboy boots are like a smooth surface, and like even these aren't cowboy boots, but there's not much grip on the bottom of them, okay? Snow boots, what kind of sole do you think they have?
They're like bumpy.
Yeah, it's bumpy, rigid, to where it creates more friction with the ground. Okay, let's go ahead and turn the page. Page 64. So everything we've talked about so far has mostly been a contact force. Besides one of them we talked about yesterday. So I'm going to read about non-contact forces. If a contact force is where 2 objects have to touch for it to happen, what do you think a non-contact force is? Kendall? Yeah, they don't have to touch. So put your finger up where it says for friction to work. Follow along as I read on page 64. For friction to work, 2 things need to touch. So friction is a contact. There has to be a contact between 2 surfaces or contact with a gas or a liquid. But there are forces that can act at a distance. They work even if the object that is pushing or pulling is not touching the object being pushed or pulled. A force that acts at a distance is called a non-contact force. So if I could stand here and push Maya just by doing that without touching her, and she went flying across the room, that would be a non-contact force because I can do it from a distance. But can I do that? No. What were some examples yesterday, without looking ahead, that we talked about that would be non-contact, that the things don't have to touch? Kendall? The magnet at the beginning. Okay? Magnetism is a non-contact force. You do not have to touch the metal thing for it to stick to the magnet. It gravitates toward it. Okay. Gravity is another one, because do you feel gravity pulling you down?
Sometimes when you jump.
Well, like right now, as you're sitting here, gravity is pulling you towards the core of the earth.
Oh, no.
Do you feel that? No, it's because nothing's touching you. Okay, it's a non-contact force that is always present. That's why when I kick a ball, even if no one else stops it, it's not going to keep going on forever because gravity is constantly pulling it down, so eventually it will slow down and stop, even though nothing physically touched it or came in contact with it. It would not just keep rolling forever. Okay, so I am at 3 examples. Last sentence, first paragraph. 3 examples of non-contact forces are gravity, electric forces, and magnetic forces. Okay, so the only one we had not discussed was the electric forces. Gravity. Every object in the universe exerts a pull on every other object. This force of attraction between any 2 objects is called gravity. Only the gravity of a large object, such as Earth, is strong enough to cause effects that we can easily notice. Without gravity, things would not fall. Gravity pulls objects towards the Earth's center without touching them. The weight of an object is just the force of the Earth's pull on that object. As an object moves away from Earth, the object weighs less and less because the pull of the Earth's gravity becomes weaker and weaker with distance. So that's why if you ever go up in space, you will weigh less. Is it that you're changing your size? No. Are you like getting skinnier as you go farther up in the spaceship? No. It's just that the gravitational pull is getting weaker because you're getting further and further away. Okay, number 5 says, draw in the box at the right where you think the feather will be by the time the apple has hit the bottom. So it shows a feather. Here's my feather. Okay, there's my feather. It shows a feather and it shows an apple. And it says if you drop them at the same time, here's the apple at the bottom. It wants to know, where do you think the feather may be? Finley?
Still floating down to the bottom?
Yeah, will it be at the bottom? No, and we can't know for sure, but we know that it would be higher. We'll just draw it right there. Higher than the apple. Does anybody know? So draw in the feather. Does anybody know what forces might be acting upon the feather?
Gravity.
Okay. Is it also acting upon the apple? Yep. So gravity is pulling them both down. So why does the apple fall faster? Sadie? Okay. It has more mass, more weight. That's one. What else is different about the apple and the feather? We kind of talked about it yesterday a little bit.
Apple's bigger?
Okay, which results in higher mass. That's true. It's bigger, so it has more mass. Harper? They're different shapes. The feather, especially if it's dropped sideways, would catch more what? The air resistance, pushing down on it. The apple is more aerodynamic, where it would just kind of fall through the air. The air is not going to hold it up or slow it down like a parachute. A feather, depending on, again, how it's dropped, if it's dropped flat, it could have some air resistance kind of holding it up also, and its weight. Right above that, it says gravity with no air resistance. Feathers normally fall slowly. You don't expect a feather to fall as fast as an apple. However, if you pump the air out of a box and drop a feather and an apple inside, they will fall at the same rate because weight will not be a factor. Okay, because our weight is determined by the gravity pulling us to the earth. So they're saying if you get rid of all that air, they would fall at the same. Are we capable of performing that experiment? No, we do not have the tools. We just have to believe the scientists that wrote the book. Yes?
How would you suck the air out of the box?
We don't have the tools to do that. You're right. I'm sure there is one. Next page, page 65. Electric and magnetic forces. Electric forces act between objects that are electrically charged. Oppositely, charged objects are attracted to each other and tend to move towards each other. Objects with the same charge repel each other and tend to move away from each other. Magnets will pull strongly on objects made of some metals such as iron, cobalt, and nickel. Every magnet has a north pole and a south pole. Magnetic force is greatest at a magnet's poles. The north pole of the magnet will pull on the south pole of another magnet. The north poles of two magnets will push away from each other. The south poles of two magnets will act in the same way. Have you guys talked about magnets much? Or have you ever held two magnets together and they kind of feel like they're pushing? That means you have the south pole to the south pole or the north pole to the north pole. If you're trying to get them to stick together and they're not, you would have to flip one of them over. Okay, for them to be attracted to each other, north and south have to go together. If you have a north and a north or a south and a south, they'll kind of push against each other. Let's go down to number 7. It says, what are some forces that might affect a rock as it tumbles down a hill? So if I throw a rock from the top of a mountain, what are some forces that might affect it as it's going down?
Hitting another rock.
Okay, so I'm going to put it could come in contact with another object. Which we said could do one of 3 things. What 3 things could that do to that rock if it comes in contact with something else? Abby, tell me one.
Stop it.
It could stop it.
Break it.
Parker?
Slow it down.
Slow it down.
Ooh, I know that one.
Speed it up.
Speed it up. If it comes in contact with something moving the same direction that's heavier, it could speed it up. Or if I throw it and then someone kicks it on down, it could speed up. What other forces? So contact with another object. Harper? Gravity is working upon everything. Anything else? Sophia?
Sometimes the like wind or air is like a lot stronger on them.
Okay.
It might move the rock.
Air resistance. Okay, it depends on how big the rock is and how hard the wind is blowing. But yes, air resistance. There's one more that happens all the time. We just don't think about it. Kendall? Nope. We're saying it's already in motion. What forces are acting upon it? Nate? If I kick a kickball right here, and there's nothing, it doesn't come in contact with anything, we're saying gravity's not going to stop it. Air resistance, what else could stop it? Brant? Friction. Friction. Okay, almost any moving object is affected by those, unless it's like in a controlled environment. Gravity affects all of them. Friction, everything has some friction. Anytime you have 2 objects touching, there's some sort of friction. Cowboy boots have less friction on a smooth floor, tile floor, than like tennis shoes, but they both do create some friction. Number 8. If Earth is pulling down on you, are you pulling up on the Earth? Raise your hand if you think yes. Raise your hand if you think no. The answer is yes. Let's go back to gravity. Let's go back to gravity. Every object in the universe exerts a pull on every other object. So it's pulling on us, but we are also pulling on it. Did you know you're pulling on gravity all day? That's why you're so tired at the end of the day. Maybe that's just me, but. Okay, number 8. I'm going to write it over here so I don't have to clear it. Number 8 is just yes. Gravity causes, it's going to word it the way the book does, causes any 2 objects to attract each other. It worded it a different way in the text, meaning if I'm pulling you, you're technically pulling me too. Gravity causes any 2 objects to attract each other. Okay, don't close your book, set it aside, and pull out your notebook, your foldable that you glued in yesterday. the first one on your foldable was force. Okay, the first one on your foldable was force. So open up the flap. Looking back in the text, what is a force? Kendall, what is a force? 3 words.
It forces a push or pull that acts on an object.
We're going to write a push or pull. There can be contact force or non-contact force. The second one is motion. One word definition. Harper. Movement. A motion is just a type of movement. Next one, gravity. Bryce?
A pole that pulls you towards the Earth's surface.
And that's specific to us. You're not wrong. Finley?
Pulls us from holding up.
And that's true too. It pulls us from floating up. I'm just going to give you this one because I don't think you'd say it word for word. It's just an attraction of 2 objects towards each other. But you guys all gave me examples of gravity. Okay, gravity's pulling us down. Gravity keeps us from floating up, but it's also between any 2 objects, not just us and the core of the earth. Friction is another one that we know what it is. It's just hard to define it. Okay, because most people would say it's like what they show me their hands. They rub their hands together a lot. Like, this is friction. But it's hard to put into words, okay? So friction, the last one, is just a force, okay? Is it a contact force or a non-contact force? Contact force, okay? But we're just going to write a force that acts against an object. Okay, and usually people say it's something that slows something down. And that's because it's a force acting against it. So if the ball's rolling forward, the friction slows it down. It makes contact with that object and acts against the rolling ball, forcing it to slow down. Okay? Or if you have on basketball tennis shoes and you're running, the friction of your feet with the gym floor slows down your feet from sliding. Okay, it's acting against the slippery floor, slowing you down. Okay. Next thing, since we have time, pull out your vocab cards. We're going to go through and put a 1 on all of the ones that are for lesson 1. So when you'll need your book, just because we'll have to go through and find the yellow words. So now if you have like a quiz over lessons 1 and 2, you'll be able to pull out your note cards that have 1s and 2s on them. The old cards you can toss. So go ahead and take a second and lay your cards flat, like space them out on your desk so you can see them all. You can put your notebook away. You just need your book and your note cards or your vocab cards. Okay, now that all your cards are laid out, go back to The chapter started on page 61. Actually, we'll just keep a couple books open. That's fine. If your book's there, keep it open. If your book's closed, leave it shut. On page 61, are there any yellow words? What is it? Force. So find your card that says force and put a 1 on it. Means it's from lesson 1. Let's flip to the next page. Any more? What's next? Contact force. Do you have a contact force? Okay. So label contact force number 1. Or yeah, put a number 1 with it. Friction is next. Do you have a friction? Okay, put a number 1 on friction. Flipping through. Non-contact force. Do you have a non-contact force?
Yeah.
Okay, label it with a 1. Gravity is next. Label it with a 1. And then do you have like magnetism or magnetic or anything like that that goes with magnet or electric forces? Okay.
That's on lesson 4.
Okay, let's go ahead and do lesson 2 today. Just number the cards, I mean. We're not going to start reading, just to kind of get a head start. So I'm going to flip on over. Do you have one that says acceleration? Okay, put a 2 on the one that says acceleration. And inertia. You guys all know what inertia is. You just have never heard the word. Inertia is a 2. Are Newton's laws? Is there Newton's first, second, and third law? Yeah. Okay, those. You should have all of them. Newton's laws. There should be 3 of them. It says Newton's first law, Newton's third law. Yeah, they're all lesson 2. So put a 2 by all 3. If you have them, just stay quiet. Okay, listen, if you are missing one of those, any of those means you probably lost a card. Use one of your blank ones and copy it from someone at your table. Okay, I think that was it for the lesson 2 vocab. So put the rest of yours, gather them back up. Put them all back in your baggie. We have lesson 1 and lesson 2 labeled. Okay, we will label the rest of them when we get to the rest of the lessons. Okay, if you are missing any, take this time and make a new one. Okay, you guys do not have any science homework tonight.